Hello. Just a reminder that if you want to follow along with the full sheet of notes, and if something does indeed get cut off on this screen capture, all of these are posted on the Advanced Physics class notes page. Okay, so we're going to look at the theory behind the mass on a spring and consider developing a differential equation for it for the vertical mass on a spring. So if I consider a spring without anything on it, it's just going to be there. There's nothing stretching it or compressing it. And if I hang a mass from it, some little m, I actually stretch the spring some delta x. This brings the spring to some new equilibrium position, because if I pull it, if I hang the mass from the spring, eventually it's going to come to a stop, and it's just going to be a stretched spring. If I push the mass up some distance above that equilibrium position, then there's going to be a net force acting on the mass. So there's some F net acting downwards. If I consider stretching the spring, pulling the mass down from its equilibrium position, then the net force is actually going to be pulling upwards on the mass. Standard physics notation, this just means a surface that the spring is attached to. Now, the net force on the mass is a combination of both the spring either pushing or pulling up and the weight of the mass, if we consider that this is all done here on the surface of the Earth with the gravitational acceleration downwards. If we consider Hooke's law from the previous Khan Academy video, we can consider just a refresher here of Hooke's law. Hooke's law stated that the magnitude of the force with which a spring would pull or push is dependent upon how far the spring is compressed or stretched. And the slope of that was some kx, and we can call this the spring constant. Has dimensions of newtons per meter, force per length. If I stretch a spring a certain distance, then it's going to exert some kind of push or pull back in the opposite direction, directly proportional to that distance compressed or stretched. So if I double the stretch or compression, then the force is doubled. With this spring constant, we often consider the vector notation of Hooke's law. The minus sign indicates that this is a restoring force. It restores the spring back to its original position. Lots of stuff in nature exhibits some kind of restoring force. Specifically, this is what we call a property of elastic materials. I hope that's not getting cut off. I found that there's an issue using this 4K screen on the Surface Pro 3 using Adobe Captivate, so that's why my screen size is kind of ambiguous. So again, if things are cut off, go to the class notes page. Okay, so let's go back to our spring with the mass as it's stretched. I'm going to use a different color now. Let's consider as the mass is pushed up. That means, and we can draw some equilibrium line around this. So this is going to be our line of, let's call this y equals 0. It's not a minus y, I'm just trying to draw this line through here. As I push the mass up, then the spring is going to push back on the mass, and there is a net force acting downwards. And so this net force, let's use a different color, is equal, it's a combination of, let's treat this direction as positive and this direction as negative. We have minus mg, and of course minus ky. And that is the Hooke's law piece there, that if I push this up a distance y, that the spring is going to push back down. The F net at the bottom, there is a minus mg, but of course there is a plus ky in this section. So the F net always has this mg. And since it does, we can actually ignore it because it's always there. In a sense, I can look at it this way. If I had my spring attached to some kind of force sensor, like you have for your last experiment in the simple harmonic motion, then I could zero this out, and that mg, which is present at all points along the way, is not going to be needed. The only net force is just the k, the minus k, times whatever displacement we're looking at. So the net force in the end is just minus k times whatever displacement that we have. And remember, y is arbitrary. It could be a function of time. So this looks exactly like the horizontal spring from the previous Khan Academy videos that hopefully you've already watched. So now let's consider the whole differential equation notation. F net is always, of course, and again, I could also call this the sum of the forces, that's synonymous, is equal to the mass of an object times its acceleration. So let's further consider the mass of this whole spring, or the mass of the thing hanging from the spring times acceleration is equal to minus ky. But remember that mass is not a function of time, but a is a function of time. That's not times t, that's a function of time. K is a constant, it just depends on the spring. And y is also a function of time. And if we're only considering our vertical acceleration here, we can rewrite this as the second derivative. Actually, second derivative of y with respect to t. So minus ky, and then y again is a function of time. And then I could further simplify this, and I say that the second derivative of my y function is minus k over m times my original y function. Now, let's just look at some of our derivative rules. And this is where I consider that if I take the derivative with respect to time of sine of some number omega times t, that's inside the sine function, I get the derivative of what's inside times the derivative of the sine function. Derivative of sine happens to be cosine. So this is just a rule. This is a rule you could use for taking the derivative of a sine function that has something inside of it, some number inside. Furthermore, if I were to do it like this, d dt of sine of omega t plus some constant c, The derivative of what's in here is still just omega. So this is exactly the same as omega of cosine of omega t plus c. So that c just stays there, but it doesn't affect the derivative. Similarly, I can say that the derivative of cosine of omega t, all these parentheses that can get kind of confusing, is minus omega sine of omega t. And here is our rule, just like our power rule for polynomials. This is our rule for taking the derivative of a trig function. Heck, I may just toss out one more derivative rule here, just because this, I think, is the easiest one. The derivative of e to some number alpha times t is actually just alpha e to the alpha t. So simply put, if I were to take the derivative of d dt, e to the t, if that alpha were 1, it's just e to the t. And that's what's really special about the exponential function. It's its own derivative. But more on that later. Sometimes when we're climbing these mathematical mountains, it's nice to admire the view and see some of the other stuff that's out there. And it's a wide, wide, wide world. So let's go back to our function. So now I need something such that if I take the derivative of it twice, I get some number in front times my original function times minus 1. And so what I get here is, oh, and one note. This specifically, actually all of these, this is the equation of motion for the spring pendulum. All of this. They're just different ways of putting it. They're all the same thing. What they tell us is they give the constraints for the position function when we consider the first and the second derivative of the position function. So that's our equation of motion for this. And it just so happens that I could take, for example, if I were to take sine of some omega t and say that my y of t is that, then my v of t, the first derivative, is omega times cosine of omega t. And then my a of t is minus, I'm going to get omega squared now, sine of omega t again. And what's quite amazing is I can see now that the minus k over m is equal to minus omega squared. Signs cancel, so that the k over m, and they take the square root of it, equals omega. So that's a pretty powerful result. What this tells us is that heavier mass means, now it's a bigger m, means a slower omega. Again, that was the angular frequency. And then stiffer spring, that's a larger k, means a higher angular frequency. So if I put a heavier mass on a spring, it's going to oscillate slower. If I use a stiffer spring, one that can exert more of a restoring force affecting a bigger acceleration, then I get a faster oscillation. And again, I see this, recap, that the equation of motion places constraints on this. And then I find the equation of motion from considering what is the F net on the mass. So that's the free body diagram for the mass on a spring. The F net is really just the minus ky from Hooke's law. The equation of motion tells us that my position function is going to be some kind of sine or cosine. You can show yourself that you can set y of t as some cosine of omega t, and that works just the same. And the result, we learn something about how to affect faster or slower oscillations. All right, so until next time, the next one will be about the string pendulum moving back and forth.